complex fraction to no longer complex fraction, right? What's the jump that they make? Now go ahead. Patricia and Kevin, you're both saying it. What do I multiply by? There are two different denominators. I have to multiply by both of them, on top and on bottom. And what happens when you multiply on top? Who cancels out for that guy? Who's left? Ah. When you go here, who cancels out on bottom? That guy. Who's left? Oh. And on bottom, what's left? All of them. That's the step they do. And that's how they're able to simplify complex fractions in their heads. Ooh, mental math with complex fractions. Go team. Uh-oh, my one's not checking homework. You're making me scared. You're making it super obvious. Then what? Don't kill a seal. Reduce. Get. Ooh, there was a jump in here. There was a jump. This canceled out with that when we distribute the negative. This canceled out with that when we distribute the negative. And we had a negative h left over. Where did the h go? Yeah, they reduce top and bottom, so then you just have a negative 1 over, and you plug in 0. You end up with x minus 1 times x minus 1 squared. Okay, 47 and 49. How did we do? Did we make it? We're able to check it in the back of the book? We're okay? Any other questions on difference quotients? So if I were to give you a quiz on a difference quotient, you guys could do it? Really? Workspace, let's go. Workspace, let's go. Workspace. Everybody same page, whether or not you did homework last night, which you should have done. Yeah, left over from the pancake breakfast. Shh. I just want to see what you can do. Workspace. I want workspace. I can't check your notes really quickly because you'll be taking notes. Yeah, let's do workspace. Let's actually do workspace. Do you have it, Victor? All right, do it in your notes. Do it in your notes. Maybe like a separate, no. Yeah, just do it in your notes. But Joseph, thank you for going to your workspace. When's WAP? Tomorrow? Oh, it's next week. Okay, you ready? I'm giving you the formula, spoiled rotten. I'm giving you the formula. I want you to evaluate the difference quotient for f of x is equal to 7 minus 5x squared. Just in case you know a shortcut, don't do it. Just in case you know a shortcut, don't do it. Do the difference quotient. If you don't know what I mean by shortcut, you have nothing to worry about. Do like we do in class. I did not give you a crazy one. No complex fraction. No nasty square roots or conjugates. I should have made it a little bit meaner. That's okay. Ready? Final answer, negative 10x. Yes? Go team! How much work did you take to do it? A lot more than that. How much work did I take to do it? taking longer than it should, but that's okay. If you're bored, go back to number 47, 48, 49, 40, 50, 40, 49, 50 and see if that little trick could work for anything else. But for the rest of you guys, here we go. How should you have done it? The limit as h approaches 0 of f of x plus h. Remember, x plus h needs to go where? Inside the independent variable spot, inside the input spot. So for f of x plus h, input x plus h, so 7 minus 5 times input x plus h squared minus f of x, who is 7 minus 5x squared, all over h. Did anybody kill a puppy? I need someone to help them out? What do I mean by killing a puppy? What am I referring to? I need to square. In order to square, I have to do x plus h times x plus h. So that'd be 7 minus 5x squared plus 2hx, or xh, either way, plus h squared, minus, don't kill a seal, what am I referring to? Distributing the negative. Then I would have had the limit as h approaches 0 of 7 minus 5x squared minus 10hx minus 5h squared minus 7 plus 5x squared, at which point you hopefully would have seen that the 5x squareds cancel. The 7's cancel. And these two terms, what do they both have? An h. Cancel it out. Negative 10x minus 5h all over h. What happens to those h's? Gone. Why does the limit now disappear? Because I'm plugging in. But I'm only plugging in for h. And what's my final answer end up being? Negative 10x. But this cool little trick that I did, it's something called a basic derivative rule. Because this thing that we've been doing is actually called the derivative of f at x. And for well-behaved functions, derivatives can actually be found with these basic rules that show something like, given f of x is equal to x to the n, f prime of x, the snazzy name, or the shortcut notation for that big old long limit of a difference quotient, will always be bring down the n, keep the x to the n minus 1. And a special application of that is actually combining another basic rule that says if you have some constant in front, like 5, you can go ahead and bring down the n, keep the constant x to the n minus 1, which is what I did. I brought down the 2 to join the negative 5. And then I had x to the 2 minus 1, which ended up being, wait, but what about the 7? This rule doesn't work with the 7, does it? Can't I make 7 x to the 0? True? And what is this nice, spiffy, basic rule that you guys haven't seen until today, most of you? Unless you went looking for it. What does this nice, spiffy rule say? What would you do to the 0? Bring it down. What happens when you bring down the 0 to multiply by? The whole thing becomes 0. Does that work if you put a 0 in there? Yep. Dun 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 dun. Ha! But don't worry. It's important to know how to do the difference quotient as well. How do we do? How many of you guys got 100? How many of you guys just needed like a couple corrections and we're almost there? How many of you guys didn't even start it? Don't put your hands up, I don't want to see. Okay, so, difference quotient. Hold up your spirals really quickly facing me. Hold up your spirals facing me with the problem that you just did. Wait, hold up. You silly goofs. What were you thinking? Hold up. Where's your homework spiral? How are you doing homework? Oh, dear. Box your final...
What?
That's not finished.
There's one last...
Pause. Listen. If you randomly stop writing a square root, everything changes. I need a limit, a limit, a limit, a limit, and then you're allowed to write the final answer of negative 10x. You have to write the limit or else I'm taking off points on the test. You have to write the limit and the limit and the limit and the limit, and you're only allowed to stop writing the limit there. The limit, the limit, the limit, the limit, write the limit. Okay, all right, I see the limit. I need the limit, the limit, the limit, the limit. Then it's allowed to be gone. That makes sense? Let me see. Oh my God. That's awful. I need the limit, the limit, the limit, the limit. I know, but technically you still need the limit. The limit, the limit, the limit, because there's still an H. The limit, then you're allowed to stop. Let me see. I need the limit. Then it's allowed to be gone. Nice. I have napkins on the front table, I think, if they're still there. It's kind of okay. This something weird is going on there. It's like a division-y thing. Okay, limit needs to go after the equals. Limit after the equals. Limit after the equals. Oh, no limit there, because you're already plugging in. That would be wrong. Oh. It's just you cramming it in? Did I miss anyone? Okay, my people over here, I wasn't looking for limits like I should have been at the very beginning. So, were you writing it? Good. Were you writing it? Good. Were you writing it?
I was writing
Good.
the entire time.
I need a limit right there until you plug in. Yeah, just right there. Okay. Okay. Huh? All right, section 12.3 tangent line problem, here we go. Section 12.3 tangent line problem, here we go. Why did I just walk around the room and say limit, 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 limit? Because I've been telling you to write them, and you guys just noticed that like 1/3 of your class stopped writing them. Question. Am I allowed to do something like y minus 3 square root of x plus 4 equals all over 2 equals 1. Am I allowed to, in getting y by itself, just randomly on the next step be like, you know what, I don't like the square root, so I'm just going to stop writing him just because he's ugly, or he takes me more time? Can I stop writing him? Why not? He still needs to be there. I still have to take the square root, and if I stop writing him, I might forget I'm supposed to take the square root. So I don't randomly change it. I don't randomly just leave it off. I keep on writing it until I don't need to write it anymore. I keep on writing it until I don't have to write it anymore. Now, this wasn't the greatest example because the square root stays the whole time. But with limits, eventually, are you able to stop writing him? Because eventually, hopefully, you can plug in. And once you can plug in, the limit can disappear. But if there's still an h, like in the difference quotient, that limit should have still been there. Okay, notes, tangent line problem. You guys got this down yesterday. A couple things I want you guys to see. First of all, tangent line. The dilemma is the slope. The dilemma is the slope. And we talked about it yesterday. The dilemma is the slope of the tangent line because we've always talked about how slope needs 2 points. But all of a sudden they're saying, wait, we have to be able to do it at 1? That's impossible algebraically. Or is it? We'll get back to that in just 1 second. But first of all, so if the tangent line is about the slope, do you guys understand at these just randomly selected points, do you understand why the tangent lines look like they do? Does it make sense? If it has to skim the graph, does it just make sense, the visualization? This one, if you were to skim the graph, it's actually going to be really, 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 really close to the graph because this is almost linear. But if you were to zoom in, zoom in, zoom in, zoom in, zoom in, zoom in, it technically only perfectly hits at this one point. It would be like very, 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 very small decimals off for a little while because this is almost linear. It technically has a little curvature. But to skim, it looks like it's almost on the graph, but all of a sudden this one's skimming. Oh, nope, nope, there's variation. I see it. This one's skimming. Oh my goodness, super obvious. This one's skimming. Oh, it's starting to look like a line again. Skimming, skimming, skimming. Does the skimming make sense? Okay, tangent line hits in how many points? At least 1 in the local region. Local is the region right around it, in the local region. Now, another note. On this one, the slope of the tangent line, let's do m with a little t below for right now. M with a little t below. M sub t, slope of tangent. I can't tell you what number this is. I can't tell you what the slope actually equals as a number, but I can say it's greater than 0. Why can I say that? It's not flat, so it's not 0, but why is it greater than 0? What's going up? Okay, so you could either say the function is increasing. That's one way of saying it. The function is going up. The function is increasing. But the slope technically isn't going up. The slope is positive. So I could say the function is increasing, or I could say the slope is positive. I could say m sub t is positive. Now, Kobe, you could do something like, oh, it's going uphill. What's it? Careful. It's a dangerous word to use in math. But you could say the slope is positive because, if you wanted to explain it to someone like in Algebra 1, because that's an uphill. I guess you could say that. The rise over run is going to be a positive. Or you could say f is increasing. Question, what can I say about the slope of the tangent line even though I don't know its number for the second graph? Less than 0. And if you were describing it to someone, you could say, well, because f is decreasing, that's one way of saying it. The function is decreasing, so all the slopes will be negative. Oh, interesting. Or I could just say the slope itself is negative. Or if you were describing it to someone like in middle school, yeah, that's a downhill slope. That's a downhill slope. How about the third one? Good, equals 0. Why? Because it's flat. And every horizontal line has a slope of 0. Wait a minute, what's so special about this point? That slope is 0, and that point, that slope is 0. They're both 0. Ah, they're vertices. Interesting. Maximums and minimums always will have slopes of 0. Well, if they're curved. What if it was a sharp point? Is that going to have a sharp point? Maybe the slopes are like clashing at a sharp point? Does anybody know like a function that has a sharp point for a min or a max? Because like cubics and quartics and polynomials, they all have nice smooth turns for mins or maxes. Absolute value of x. Not a competition, but good job. Okay. What's the slope at a sharp point? How do you skim at a sharp point? Well, first of all, what's the slope at a point on a line? Because that's kind of funny, absolute value of x. We haven't really done any tangent lines to lines. What do you think the slope would be here? Not a number, but how would we find the slope? How do we skim right there? Couldn't we just say this is equal to y equals 1x? And so couldn't we just say that m of the tangent is just equal to 1 because it's on a line that has a slope that I can know? Does that kind of make sense? Y equals 1x because of this function. Remember, we can rewrite this as a positive x sometimes and a negative x sometimes. If x is a negative number, if x is a positive number. Piecewise definition of an absolute value. Anyway, coming back. What would be the slope of the tangent line at this point, or at any point over here? Negative 1. Good. So we have negative 1 coming in, positive 1 going out. Well, wait a minute. What's the slope at the sharp point? How do you transition from negative 1 to 1, or do you? What would happen if I approached and went to negative 0.01 and negative 0.001 and negative 0.0001 and negative 0.00001? Guys, what are all the slopes on this branch of the graph? All of them are negative 1. Well, stink. Okay, well, what if I come from 0.01 and 0.001 and 0.00001 and 0.00001? What are all the slopes on this side? Uh-oh. Didn't I? Oh, maybe I haven't said it yet. But what seems to be happening as I transition from one side of the graph to the other side of the graph with the slopes? Are they in agreement? If I was to come into this one, the slope right before would be very, 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 very small. As I keep on getting closer and closer and closer to this point of tangency, to P, who's this guy down here, as I keep approaching, the slope will be getting closer and closer and closer and closer to 0. As I come from the other direction, the slope will be getting closer, 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 closer to 0. They're in agreement, so the slope is 0. But that one, they're not in agreement. Guess what? The slope is at the min on this one. Guess what the slope is at the min on this one? Wait a minute, what does this sound like as you come from one direction and from the other direction, if they clash and if they don't agree, and as we approach and approach and approach? Wait, what approaches? A limit. Huh. I wonder if limits are slopes of tangent lines, or slopes of tangent lines come from limits. Anyway, moving on. This is going to be a relative min. Let's not really put any other descriptions on that one. Okay, let's keep going. Choop, choop. Dilemma, slope needs 2 points. Dilemma, slope needs 2 points. The old-fashioned way of talking about it, M needs y2 minus y1 over x2 minus x1, which is technically the same thing as delta y over delta x, which could technically be f of x plus delta x minus f of x all over delta x, if we were to try to get this in some sort of snazzy notation. Saying, okay, if we're going to move a delta x away to get to another point, well, I guess we could have f of b moving that delta x away to get to the new point. So delta x says, how far away is x2? Cool, I need the y at that how far away is x2. So that's how we would normally solve. Now, you guys probably haven't seen this notation very often, if at all. But you have seen delta x representing the change in x. So the idea is I could do f of x as my y1. y2 would say, hey, go a little bit away from x to get another point. And however far that away is can be my delta x. That's basically saying, okay, cool. Slope at 2 points. The slope needs 2 points. Now, if they were to give us this graph that you see down below, I'm going to zoom in on him just a little bit. If they were to give us this graph down below and ask us to visually try to approximate the slope of the graph at 1, 1. Now here's where it gets weird. At 1, 1 is 1 point. All they've given us is 1 point. We would call that a point of tangency. We could look at this graph and say, well, the only way I know how to do slope is a rise over run. So if we see the tangent line, we can say, okay, that looks kind of like a point. So we could estimate, we could eyeball another point on the line. If we can see the line, we could eyeball another point on the line and say, okay, it looks kind of like the point 2, 3. This point's obvious. This one's the point 1, 1. They gave it to us, first of all, and second of all, I can see it. So if they draw the tangent line for us, or if we draw the tangent line and are pretty confident that we kind of drew it correctly, we could kind of eyeball a secondary point and say, ha-ha, then now I can use my nifty-difty formula that says, let me show you what the nifty-difty formula says. This really simplifies down to that, so let me show you the hard version first, then we'll make it easy. Guys, what's the distance between the first point, the horizontal distance? What's the horizontal distance between the first point and the second point? So I could say that if I'm thinking about my delta x and my f of x plus delta x, trying to make sense of this formula, I could say delta x, how far away were the two horizontally? 1. So I could start with my original x value, which was 1. I could add the how far away I got for my secondary point, which is 1, and I could subtract f of 1. This ends up being f of 2 minus f of 1 all over 2 minus 1, which we already figured out was 1. So it's the same thing as doing y2 minus y1, just kind of a snazzy way of showing it. And the only reason we plugged in 1 is because that's how far away the point that I was able to eyeball. That's how far away the point was from the original point, horizontally speaking. So who is f of 2 or y2? 3. And who is y1 or f of 1? 1. So my best guess, just eyeballing the graph, is that the slope of the graph at the point 1, 1, aka the slope of the tangent line, is 2. Visualizing is 2. Now, the nice thing is this function, this graph, is actually super, super nice and super, super easy. But let me show you something super, super cool that your calculator can do. Ready? I want you guys to go ahead and put in the function y equals x squared. X squared. Go ahead and try to get this portion of the graph on the screen. I think Zoom standard should more than suffice. I wonder if we can ask the graphing calculator how to find one of these slopes for me at a point. That'd be snazzy. We can ask the calculator how to, let's see, find a value, find a 0, find a min, find a max, find an intersect. Hey, didn't we look at just a second ago on in our book with the difference quotient problems? And didn't we see this little curvy essay thing next to the calculus section problems? It's called an integral. This one right above that one, because that one looks kind of advanced. This one right above that one, dy dx. Doesn't that kind of look like delta y over delta x? Just kind of. But what's weird? There's not a delta. These d's in calculus actually stand for differential of y. Differential y over differential x. And what this dy dx stands for isn't just any old delta y over delta x, which would have us go from one point to another point on the curve. It actually says, no, I want the change in y over change in x of a tangent line, not the function. The function can use this old formula. I want it of the tangent line. So this is kind of looking like a slope. There's a snazzy little d thing that's been brought in. Some of you might hear about differential calculus. That's the d differential. Anyway, hit number 6. What's it asking us? Nothing. Oh wait, it doesn't ask us anything for value either. Maybe we just need to plug in the point. Guys, what point were we supposed to be plugging in? 1, 1, right? Oh, it only asks for x? Okay. Enter. Hey! That's kind of snazzy. I wonder if that's right, and the answer is yes. So my estimation was pretty stinking good based on eyeballing the graph for this problem. It's not always going to be stinking good. Because let's just say we change this just a little bit, okay? Let's say we change this to be, here's one. Let's say I was to do it at, instead of finding or using the tangent line at 1, let's say I was to do something like 3/4. So let's do it again. Second, calc, let's do number 6. Let's say I was to do it at 3/4, so 0.75. I wonder if this one's going to be as pretty and as nice. If I was to go a little bit before and do a different tangent line, I wonder what that slope's going to be. Oh, 1.5. I don't know if I could have eyeballed that quite so well. Or we could go ahead and say, what if I wanted to find the slope at something else like 0.37? Huh. Has anybody seen a relationship with all of these slopes? 0.37 became 0.74, 0.75 became 1.52, or sorry, 1 became 2. We can make it a little bit easier and we could do something like, hey, what's 3 going to become? 3 is going to become 6. What's, I don't know if I could do it, but we could try. What's 5 going to become? What do you guys think? Yeah. Oh, that's weird. What's going on with all of these slopes? They're all just doubling the x value. Doubling the x value, that's weird. Guess what would happen if you guys had done the limit as h approaches 0? Who's this guy? Isn't this the limit of the difference quotient? And didn't I tell you that he was a super snazzy f prime dude? Guess if you had done this, you would have brought the n down. is the difference quotient limit, which is really called a derivative, actually telling me the pattern as to how to find all the slopes of the tangent lines? And the answer is yes. That's cool. Let's keep going. So then, I kind of showed you some of the stuff on the page before. But what's different is they're trying to make it easier on your brains and not get you too confused. So what they say is, you know what? Let's let that delta x that's kind of confusing and a little bit messy and awkward, can we make him an h instead? Let's take that delta x and let's make him an h instead, because delta x might get confusing with x, and you might try to square stuff when you're not supposed to because they're two very, very, very different things. So then they say, let's just make delta x into h to make things a little bit easier on the brain. Then we can take that whole change in y over change in x, kind of like I was showing on the page before, and not have to worry about the delta x looking quite so messy. We can use that to go from one point on a function to another point on a function. Remember the dy dx, that was special for a tangent line. That only kind of worked when we could see the tangent line. And that's not always a good way to go. So to do the actual delta y over the actual delta x, we would need to do this difference quotient, which you guys have already started working with. In order to get to here, we would take our y2 minus y1 all over x2 minus x1. If you guys notice, the x's cancel. We just end up with our delta x, or our h, left over. And on top, we have that f of x plus h minus f of x. And all it's doing is saying, hey, for two general points, one that we start with, that's our point of tangency, and one that's a little bit removed, we plug in that x plus h to get the y. We can go ahead and do a quick little average rate by simplifying. We can say, hey, this is just talking about the slope of any secant line. Tangent hits in 1 point, secant hits in 2. And then with calculus, we say, psh, we can take a limit. We can make the secant line tangent line. We can take the limit as h approaches 0 and see if the values seem to be converging to an actual number. And if they converge to an actual number, booyah, that's the slope of my tangent line. So ironically, you guys did the very math necessary for this section at the very end of last section. You guys did the math necessary for this section at the very end of last section. Now, you could write down the next page. I don't know if you need to. You kind of saw a picture earlier on when we did the tangent line problem really quickly. The idea is, hey, if we make the h get smaller and smaller and smaller and smaller, if we have the secant lines approach, 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 if we had the secant lines approach, meaning the secondary point, get closer and closer and closer and closer, aka my h is approaching 0, all of a sudden these secants are going to get closer and closer, converging to the actual tangent line. So what this is showing is, hey, as that h diminishes, as my points get closer together, I'm going to keep on converging or approaching the tangent line. So I don't know if you need the picture. I don't even know if you need the paragraph, but the idea is let's get closer and closer, and the way to get closer and closer is right there. So with that, you don't have to write down this one. This one's going to be an illustration that we can look at. I want you guys to write down this box right here. Let me zoom in. To find the slopes of any graph at 1 point. To find the slopes of any graph, specifically talking about the slopes at 1 point, not the average slopes, not the average rate, but the instantaneous rate, aka the slope of the tangent line. we had this following definition. M, which if you want, you could put a little m sub t. That's what we were calling it. M or m sub t, the slope of the function. That's what they're saying. The slope of the tangent line is what they're going to define to be the slope of the graph or the slope of the function. It's going to equal the slopes of the secant lines as h approaches 0, which the secant lines are really just the difference quotient. The snazzy notation, the slope of the tangent, has its own special notation. That own special notation, f prime, not f apostrophe, f prime of x. You use the apostrophe as a symbol, but we're going to say f prime. It's not f to the 1, it's a little apostrophe. F prime of x is the special notation for the slope of the tangent. And it's found by taking the limit of the difference quotient that you guys saw last section. So here's the crazy thing. Is there any new math to do? And the answer is, not really. We learned how to do it at the end of yesterday. We just have a little bit new meaning to what we were doing, because now we say, oh, that hard problem that we were doing yesterday, the limit of the difference quotient, it's really us finding the slope of a tangent line. It's really us finding what we're going to eventually define to be the derivative, which is basically the whole first semester of calculus. Don't worry, this one type of problem is not the whole first semester, but learning what a derivative is and how it can be used, and how to do shortcut rules like the one I showed you of bringing down the n, and how to use shortcut rules to tackle harder functions. That's the first semester of calculus. Now, we are going to see a couple things tomorrow. I guess we'll still need to finish up a little bit of 12.3. But if you guys notice, if it says in an example to find the slope of the graph, f of x squared at the point -2, 4, do you realize that we're just going to go ahead and do the limit as h approaches 0 of f of x plus h minus f of x all over h. And the only additional step is plug in x equals -2 at the end. So isn't this yesterday's homework? Isn't this 2 days ago homework that we just got stuck on? What's new? Plug in at the end when you have your little equation. And if some of you guys want to be like, she told us a shortcut rule. Cool, do it the long way and check it with the shortcut rule and then see if you're right. But can you get started on homework? Definitely. Will this take us long tomorrow? Definitely not. Because all we need to do is basically say, hey, now we just have a new way the problem can occur. Instead of them saying take the limit of the difference quotient, they'll say find the slope. And we'll talk about a few terms like derivative. All right, cool kids. Start 12.3 tonight. Let's see if you can get far at all, and I'll come back with you guys tomorrow. Happy Wednesday. Just kidding. Happy Wednesday.